Right? Now remember now, like last time, we said we were forming an acylium what? Ion, like in our step, in our step 1, right? And then we ended up with these two resonance, structures, right? Now that we've formed our acylium ion, now, like, it therefore becomes what we refer to as a what? A very strong, what? A very strong electrophile that can now react with what? With our benzene, right? With our aromatic ring, right? Now, there's our carbon atom here, double bonded to oxygen, 1, 2, 1, 2, right? And then this one is our CH3. Then now, like, remember now, our carbon now, like, is what here? Positive in charge, right? Now there's a strong electrophile. We've got a strong electrophile now. This strong electrophile now, like, will now be attacked by what? By the benzene ring, right? So if it's going to be attacked by the benzene ring now, like, what then do we form? You see, this is our next step now, like our second step. Now, what then do we form here? We form this here, there we go. This here, right? This here, that here. A new bond now, can you see now, to this carbon atom, which is doubly bonded to what? To oxygen, 1, 2, 1, 2. Then this one goes to what? To CH3, let's just put it that way. Okay, let me rather put this carbon as a line instead. Right, there we go, double bond, this here. There's our oxygen. What call that? Now, there, O-M-E. So, the addition here is now directed by what? By the methoxy group that directs ortho or what? Or para, right? So there's our para. That's it. The addition is directed to this now. Remember, this is our target molecule in this case, right? So this is what we're going to have. Sorry. Then here we no longer have a double bond here, right? Because the double bond has been used. Now, it means that now, like, between these two carbon atoms, then one carbon atom becomes what in charge? Positive, because it has lost that bond, right? Now, remember here, you had a hydrogen atom here. You had a hydrogen atom. So we generate this ion here, in this case, right? Now, recall now, like, we've got a positive charge, single bond, and a double bond. Then this charge now is going to be resonance stabilized. Resonance what? Stabilized, because it's a charge, single bond, and a double bond, which is a source of electrons. So these now, like, will move. There's mobility here of this electron cloud to come and form a double bond there, right? Now you generate another resonance, what? Hybrid structure there. This, that, this here, this, that, in this case, here, oxygen, this is Me, 1, 2, 1, 2, isn't it? Now, and then now, like, we've got what here now? We've got a double bond that is here, a double bond that is here, and then in that case, we have this, that, double bond O, this, 1, 2, 1, 2. Then the double bond now, like, is on this carbon atom here. Right? Very good. And then what happens thereafter now? Again, a charge, single bond, double bond, a source of electrons. This here, these electrons here, they are going to be brought in where? Here, to stabilize the charge. So there's going to be mobility. We form another resonance structure. That side. Let's see. This, that, this, that. In this case, there's our O, M, E, 1, 2, 1, 2 there. And then we've generated a new bond here. Double bond here, sorry. Then there's the old double bond that was there. This, that, double bond here, this here. And then I'm like, where's the charge now here? There's the positive charge. Right? Very good. Now, here I've got a positive charge. Single bond, single bond, single bond, single bond. Then I can no longer move this side. I can no longer move this side. Then I can close that side. Isn't it? I can close that side. Right? Now, can you see here now, like, I can even have another option in this case, because there's a positive charge, source of electrons, and a lone pair here. Here, I could have another, what you call like, resonance structure here that I can form. So this one, if I were to say this is A, right? I could say this side it's the A option to yield this structure. I could say this is my A option to yield that structure. Or I could have had like here, this one coming here. I could have this one as a B option, meaning that I could have this here as a what? Double bond here, oxygen bonded to Me here, one lone pair. Now, can you see that down there? And a positive charge on this oxygen atom, isn't it? And then what do I have? What do I have then now? What do I have then now? In that case, I've got this here, this, that, double bond O, this, 1, 2, 1, 2. I'm just for an example. So I end up with many resonance forms, isn't it? Right? So this is what I have in this case now. Right? Now, last step, I am going to choose from these 4 resonance hypoid structures. In fact, I could take any if I wanted to, but for my case, then it's better to take the resonance structure that is closer to what I want to form. In this case here, this is what I have. There's my aromatic whatnot here, this double bond here, this, that, double bond O, 1, 2, 1, 2. This here, there's a proton here, then the positive charge is on this carbon atom, and then here you've got your OMe, 1, 2, 1, 2. Remember, in that example, when we generated this, we still have that AlCl4 minus that we formed that side. We don't forget that, right? Now, that AlCl4 minus, it comes in now. Al4Cl4 minus, then it comes in to pick up this proton. As this proton leaves behind the bond pair that it shared with this carbon atom, then that bond pair is used now to reform, right? The what you call like the aromatic ring. There we go. Double bond, double bond, double bond there. There's your OMe here, 1, 2, 1, 2. This here, double bond O, this 1, 2, 1, 2. This now is your target molecule, right? So your AlCl4 and H will give you HCl as a byproduct and give you what? AlCl3. To show you that now, like whenever you start with a catalyst, a Lewis acid catalyst, remember a catalyst, right? It speeds up the reaction without itself taking part in the reaction. Therefore, you started with an acid, you must end up with an acid. That's what we mean now, like, you know, like by this, what we call like a Friedel-Crafts isolation. Remember now, another thing that is important here. In a nutshell, with your benzene chemistry, right? Your benzene does not want to react. You want to force it to react, right? And when it reacts, it undergoes electrophilic aromatic substitution, right? Where one proton is substituted by whatever group, right? So initially here, you had a proton that was hydrogen. Yeah? If we go back to the economics of this reaction, so there was a proton here in that position. Now, is the proton there now? No. The proton has been taken out You have seen that? And then something else has been added on that carbon atom. Or I mean like in that same position. Right? So the type of reaction here now, like it's what we refer to as an electrophilic aromatic what? Substitution. Right? So in this reaction here now, like you see, like if you are asked a question, right? There's your target molecule, then you must design, right, a synthesis as well as a what? A retrosynthesis. I'm just making an example. Let's say now like ask out of 10 marks or 12 marks or whatnot. You see, so this is how you do it, right? Thank you. Don't fear. Organic chemistry is easy. Organic chemistry is beautiful. Organic chemistry is fun. And the more you do it, the more you will be better at this thing. Okay? I'll see you in the next class. Thank you.